that is
maybe I should welcome Jose for this bi-weekly course to assist. And if you're ready to start, Jose, I would
yes.
like to hand you the floor for the coming an hour and a half. And to everybody listening, please ask your questions and try to join the meeting as actively as possible. All right, floor is yours, Jose.
Okay. So I wanted to ask you first to okay, let me share the screen. Okay, so so the lecture today is about finite element analysis. Then I will start basically with the fundamental concepts of finite elements for elastic solids, and then I will move into an application. So an application of a finite element within the context of biomechanics. No. First of all, before starting, I wanted to run a test, okay, a small quiz. Then I will ask you if you can install Kahoot in your cell phone. I think you already did it because we use it for another activity in the past. Okay. So if you can actually install this Kahoot, I will show you. Okay. Okay, Kahoot. You can actually look it in the app as just as a Kahoot. Okay, it's written like this: K-A-H-O-O-T. Okay? And then we can start running. We'll ask you a few questions regarding finite elements now at the beginning of the presentation, and then 3 more questions at the end, just to see if you were actually following with attention. Okay? So please let me know when you install the app, so we can start with the game. Okay, it's a very it's a quite quick game. So you let me know when we can start with the game. Okay. Just give me a couple of minutes more. Yeah, the pin code will come now. Okay, so can we start? Okay, so I will start with the questions. Okay. Choose a way to play this Kahoot. Let's see. Oh. Okay. Okay, this is the pin number. Okay, I will start.
Can we log in online, Jose?
Sorry?
Can we use it online on the website?
I don't know.
The pin is not working for me.
Yeah, I guess.
I'm using the web.
I think you can use the web also, yes. If you actually, if you type Kahoot, it will take you by default to the gaming part, so where you have to input the pin. Okay, shall we start? Okay, Beruts.
Yeah.
All right, so we start. First question, a very simple one. Okay. Okay, at least you're familiar with the name of finite element method, okay? Let's go to the second one, which is a little bit more complicated, okay? Well, yeah, it's fluent. Fluent is a finite volume method, not a finite element. Okay, Adina, ANSYS, and FIB, they are all finite element codes. Okay. Oh, I thought I had assigned no points, but anyway. Who is this guy? This is a difficult one. A very important person for finite elements.
That was a good hint.
It's Galerkin. Great. And then the last one. When FEM was born. And this is the example for the first FEM calculation in history. In 1943. Excellent. Okay, guys, I think you're ready for the finite elements then. Okay. All right. So, Beruts, you were the champion. All right. So I will start with the okay, with presenting what are the contents of this presentation. So I will start with a brief history of the finite elements because it's something I really always like to do when introducing a topic. And then I will talk about basically what is finite element analysis, which are the basic steps, and give you some hints about what is important to consider or not in a finite element analysis. And then in the second part, I will discuss an application applied to biomechanics. So the finite element methods is basically a numerical technique that allows us to find an approximate numerical solution to a mathematical model of a physical problem. Right? So this sounds a little bit complicated, but it's exactly what we do. Okay. So before starting to describe all the steps that are behind the a finite element analysis, I want to give just a brief history of the evolution of this very important tool for us. No? Okay, so everything started in the end of the 1600s with these two guys. Okay, one is a Dutch guy, Jacob Bernoulli, and the other is Leibniz. Okay, so everything started with these two guys with a very simple problem, not a simple problem, with a problem that was posed by Johann Bernoulli, was Jacob's brother. In solving this, what he called the brachistochrone problem. This problem was initially posed by Galileo Galilei, and it considers basically the gliding of a particle without friction, just an impulse or driven by the gravity from point A and point B. And the question is to describe which is the curve, okay, the trajectory that this mass will describe in performing this act, no? So let's see that this problem was proposed to the community in the 1696, okay, by Johann Bernoulli in Acta Eruditorium, was called the name of the journal. And then this problem was responded 1 year by 6 persons, okay, where Johann Bernoulli, Jacob Bernoulli, Leibniz, Newton, that actually respond to this problem anonymously, and 5 persons, excuse me, and L'Hopital, okay? And in particular, the solution from Jacob and Leibniz was very important in this problem because Jacob, when solving this problem, introduces the variational calculus, okay, which is actually what is behind of the finite element formulations. And Leibniz solved this problem using an approximate discrete solution. So let's see that Leibniz was given the first steps on introducing what later became the finite element method. Okay. We had to wait, however, almost 200 years, okay, to see the first application of a discrete method to solve a structural problem. Okay, and the first well-known and well-established method was proposed by Rayleigh-Ritz. So Lord Rayleigh was an English scientist, and Walter Ritz was a German. Basically, Walter Ritz was who proposed the model, the method as we all know, that we know as the Rayleigh-Ritz method. Okay, and it was used just to calculate the deformation and the vibration of plates. Okay, basically this was not exactly the finite element method that we know today, but it establishes the basis, okay, of the mathematical notions behind the finite elements. Okay, and in fact, when we start studying every single course in finite elements, it starts by describing the Rayleigh-Ritz approach, the Rayleigh-Ritz method. Then in 1915 appeared this guy, Boris Galerkin, which was an engineer, a Russian engineer, and he introduced the method, the Galerkin method. Okay, the Galerkin method has basically key importance in the development of finite elements because it's the method that allows us to find the integral, formulation of a or the weak formulation, as we call in finite elements, of a boundary value problem. Okay. So his ideas were then basically applied by this guy. This guy is Richard Courant in 1943. And he was the first in solving a structural problem using the finite element method. He didn't call it finite element. He called it finite sub-elements, subdomains, finite subdomains, or element subdomains. And with the idea that basically he discretized the geometry of interest using these small subdomains that were composed of triangles and quadrilaterals. The problem that he solved for the first time was this square section of basically, this is a Saint-Venant solid subject to torsion, okay, with a hollow square section. Okay? His paper was published in 1943, as I told you, and was basically the first known finite element application to structural problems. Then we arrive to the modern times. So the modern times is basically where the actual finite element method was established and was developed. Okay? And then the guy that you see in the top left, no, in the green square, is the one that coined the name finite element method to the tool that we use today. His name was Ray Clock, and was a professor, mechanics professor in Berkeley. Okay? And actually, UC Berkeley is considered, together with two other universities in Europe, in the University of, where, I don't remember if it's Munich, where the professor Argyris that you see here in the left was working, and Professor Oleg Sienkiewicz that was working in Swansea. So these three centers now in UC Berkeley, that was the work base of the work by Ray Clock, and the work of Edward Wilson that you see here in the right. These two guys settled basically the basis for what is known as the modern finite element method. The school from Berkeley gave very famous names as Professor Taylor, Professor Hughes, Juan Carlos Simó, and Jürgen Bathe, that if you see, they are most of the names that behind most of the most famous finite element books. No? And of course, talking about Argyris, Professor Argyris and Professor Sienkiewicz. So those four guys are basically the cornerstone on which the finite element is based. Okay. So you will ask, who is this guy in the bottom? No, anybody recognize him? Somebody knows who is this guy? I don't see the chat, so you have to open the microphone. Okay, this guy is Sergei Sobolev. I'm pretty sure that most of you have heard about the Sobolev spaces, no? And why is he important, no? Is he important because he's extremely important because finite element is, I think, is the most truly example of how an engineer intuition and application has conquered the world of mathematics and numerical methods. So what I described so far, all the applications of the on the structural analysis using finite elements until the 1970s, okay, were based on using a tool that worked fine, but we couldn't actually prove or perform any analysis on this tool. Okay, so any mathematical analysis on the convergence, on the quality of the solution, on the error bounding, etc., etc. Okay, until basically this Sergei Sobolev discovered the Sobolev spaces that allows to the finite element applications and the finite element analysis, and then to establish the truly mathematical theory behind this tool that had already been proved to be extremely useful and performing. Okay? Remember that till the 1970s, where there was not a mathematical theory behind finite elements, okay? This tool was used to make the calculations for the space, for the Apollo program, okay? So a tool that was a truly engineering based, a truly engineering born numerical tool took the man to the moon, you know? Okay, and then from the 1950s to today, basically the number of applications behind finite elements just explode, you know, just grow exponentially. And now we find finite elements analysis in pretty much everywhere. However, we have to be very careful in using this tool because, as I mentioned before, it's a numerical tool, so it has to be used with care. No? So, which are the basic steps, you know, behind the finite element analysis? So the first step behind a finite element analysis is what I call the idealization. No? The idealization comprises on basically the modeling part in which we will represent a physical model by a mathematical model. Because basically the finite element can only be applied to a mathematical model. And then it's our responsibility of modelers, you know, to basically first come with a mathematical description as accurate as possible to our physical problem, okay? Once that you establish, for instance, the mathematical models, as you can see, now this is the cat representation of my spherical tank, okay? And then I will define a set of governing equations that will basically be responsible for the mechanical response, for instance, of this structure and the boundary conditions, okay? Once that I have defined a mathematical model, then I can use finite element method to solve these mathematical problems. And then in the finite element method, we have basically two main components. No? The first one is a discretization step, okay, in which basically what we do is that we discretize, okay, we discretize my continuum problem into these subdomains that couldn't define them, or these finite elements, as Professor Clark coined these small elements that we use to basically discretize my geometry. Once that my geometry is discretized, and then I will pass from a continuum model to a discrete model, then arrive the solution part that will provide me the approximate solution to my problem, okay? And then with this solution, I will be able to evaluate how well my modeling is, okay? So in each of these steps, we have a number of uncertainty, a number of errors, okay, that are present, no? The first one, I will start backwards because it's easy just to enumerate them, is the solution error that is present in basically solving the discrete system of equations, okay? So that is, those are associated to basically the iterative solutions, iterative schemes that we use to solve the system of equations, or the direct method that we use to solve the system of equations. Then when we compare the discrete solution with the mathematical model, then we have, of course, the error that comes from the discretization step, okay? So as you can imagine, if I discretize my model incorrectly or too coarsely, of course, the amount of the error associated with that step will be significantly larger, okay? And finally, we have basically the modeling error. So the modeling error is associated to how well I'm representing my physical system, okay? So what we can actually control, depending on the different steps in each of these steps, we can control up to some point these errors that we are introducing, okay? So the modeling error, of course, is associated to basically the technology, how well we can actually describe our physical system, no? So how well we know our physical system in order to produce more and more accurate mathematical models of it. Okay, so how do we do these things? No? So imagine that I have my physical model. In this case, it's an spherical tank. So from this spherical tank, I know the operating and design conditions that will be subjected. Okay, the materials that compose my system, the fabrication process, just to say something like that. So with all this information, and the more information we have, the better, then when we can actually come up with a mathematical model of my system, okay? So first of all, we start with the geometry, okay? So basically the representation of the geometry. Then here's where you decide if I want to represent my spherical tank just by a sphere, if it's a shell, if it's a solid, if I can actually remove all the supports, or if I should include them into the mathematical description. Then comes the modeling framework. So the modeling framework comprises the governing equations, which is basically a set of partial differential equations that will basically control my solution, okay, govern my solution, and the boundary conditions. For the governing equations, if you are solving an elasticity, so a solid problem, a structural problem, okay, in solid mechanics, the governing equation in most applications is basically given by the principle of virtual work, okay, which is actually the equation that you see there. So the principle of virtual work is an equation that puts into correspondence, no, the external forces that we apply onto the solid. So those could be sort of superficial forces or volumetric forces that will actually cause a deformation of my solid. Okay, so it's the equilibrium between these external forces and the internal forces that are developed inside the body. Okay, so the internal forces are quantified in terms of the stresses that are represented by this sigma that you see here. And the deformation of the solid is characterized by this epsilon, okay? However, this epsilon that you see here in the principle of virtual work corresponds to, so in a deformable solid, for instance, we can distinguish between unstressed or undeformed configuration that is given by this blue line, okay? That corresponds to the shape of our body without any loading applied to it, okay? So when we apply the loads, so what happened with this body is that this body will experience a deformation, and then will actually move towards a deformed configuration that is indicated by the black line here. Okay. Then moving from the blue line to the black line implies that the body will be deformed and that a set of the stresses will be generated. Okay. So then you can imagine basically the stresses appears as a consequence of the deformation of the solid, okay, which is deforming due to the action of an external forces. So the other ingredient that we need to solve this problem is a law that make a correspondence, so no correlation, that make a correspondence between the deformations that they experience the solid and the stresses that are generated, okay? And this is what we call a constitutive law, okay? This constitutive law for an elastic solid is usually characterized in terms of this function W that we call an strain energy function, and that you have heard a lot in our INSYST meetings, no? So basically, depending on this strain energy function, we can, let's see, reproduce or model the mechanical response and mechanical behavior of a number of materials, okay? So different materials obey or basically can be characterized using different strain energy functions, okay? This E, big E that you see here, represents the deformations of the solid. So the deformations that the solid experience moving from the reference configuration to the current configuration. And then finally, we have the boundary conditions, okay? So this mathematical framework, this mathematical model here is what we will be using to describe the physical system that in this case is basically a sphere, a spherical tank that is that you see in the picture, okay? So once that we have defined the mathematical model, okay, then we can apply the finite element method, okay? So now what I want to do is to solve this set of partial differential equations, boundary conditions, and constitutive law, right? Of course, you can apply any, numerical method. You could apply Rayleigh-Ritz. You can apply finite difference, okay? Any numerical method you have available, okay? Finite element has been demonstrated to be a really flexible and powerful tool along the years, no? And then in this lecture, we will focus on this particular tool. So when we apply finite elements, okay, we, in the application of finite element method are actually comprised by three main steps, okay? The first one is the preprocessing step, that is a user-dependent step. And during this preprocessing, what we do is to discretize our geometry. So we discretize our mathematical model using our finite elements, okay? Then it follows the assembly and solution step, okay, that are usually performed by the software, okay? That can be a commercial software or an in-home software, okay? And basically what it does is to compute the contribution of each single element, put them together in order to basically build up my full solid, and then transform the continuum model into a discrete model, okay? After this assembly step, we impose the boundary conditions, and then finally we solve the system of equation. Okay? So this very last step here, that is actually, I just use these red letters, is a truly numerical process. And when I call it truly numerical process, is that we are actually solving a system of equations, okay? All the intermediate steps are actually associated to basically calculating components and assembly all together. Once the solution is available, we enter in what is called the post-process, okay, step, that is basically on displaying the displacements on our structure, okay, and calculating the stresses and deformation. That is basically what allows us to do all the analysis that we are looking for. Okay, so it depends on what analysis you are performing. You may be interested in the stresses, in the strains, or maybe in combining the displacements or any other output that can be computed from a finite element solution. Okay. So let's talk a little bit about the preprocessing step. Okay. The preprocessing step, as I mentioned, is the discretization step. So in this discretization step, what we do is that we transform, our continuum model. So we transform these continuum integrals here into a discrete system. Okay, so we divide our geometry, okay, in finite subdomains or finite elements. So these integrals are actually transformed in sums, okay, in sommatories, okay. And to perform this discretization, we use what we call a library of elements. The library of elements is that depending on which are the characteristics of the elements that are part of your structure, you could use 1D elements that are used to model troughs and beams, for instance. You can use 2D elements that are used to useful for modeling membranes and shells, and then later the 3-dimensional elements that are used just to model solids, okay? As you can see, these elements, in particular 2D and 3D, you have a variety of shapes, okay? Primarily, we have triangles and quadrilaterals in the case of 2D cases. And as you can see, we can have triangles with 3 nodes or more nodes. So we have what we call or linear elements of high order elements, and quadrilaterals with 4 or more than 4 nodes. Okay. The same thing for the solid elements. For the solid elements, we can have a single tetrahedrals, so pyramids, okay, prisms, or hexahedrals. What is common in all these elements is that they have nodes, faces, and edges, okay, except for the 1D element that has only nodes and edges, okay. Nodes is where the solution is actually computed. So the displacement of the structure is actually computed at the nodes, okay? Whereas the stresses and displacements, as we will see, are not computed at the nodes, but are computed at the element level. I will not enter much in detail because I have no time to do that, okay? But we will see some of the implications of this, okay? So, at the first step is the discretization, is dividing this. And this is called in the finite element jargon as the meshing the geometry, okay? So once that you have meshed your geometry, then you enter in the next 2 big steps, the assembly and solution and the post-processing step. So in the assembly, what you take is that for each element, we calculate the contribution of the element. That in a solid application, the contribution of the element is actually given in terms of a matrix KE that we call the element stiffness matrix. Okay, a vector of elemental loads, which is associated to basically the external loads that are applied to that particular element. Okay, and in the case of nonlinear analysis, is the difference between the internal and external forces, and a vector of nodal displacements, okay, element nodal displacements. If you can see these things, for an elastic solid or a deformable solid, so the element equations can be, let's see, we can make the analogy of an elastic spring, okay, in which the matrix KE is associated with the stiffness of the spring, and RE is the force that we need to apply to deform the spring U sub E, okay, UE. There's one that we have basically for each element, we calculate these things, no? Then what we do is in the assembly step, we put all this information together. So we assemble in order to create or to build what we call the global stiffness matrix, okay? The global displacement vector and the global force vector. So once you have assembled the system of equations, you input the boundary conditions and solve the system. So you solve this system of equations, and as a solution of this is the displacements at the nodes, okay? So once that you have the displacement at the nodes, then you can perform the post-processing step to calculate the displacements and the stresses and the strains in your structure, okay? So this is basically the basic steps behind a finite element application, okay? So from all these steps that I described you, okay, discretization is one of the most important ones, okay? Most of the others, the assembly, the solution, and the post-processing usually is performed by the software, okay? But in order for the software to provide you good results, you have to provide the software good meshes, okay? And this is a very important message, okay? When we do finite element analysis, it's basically like a big element to take into account. No? It's the major rule that we have to follow. Okay? So when we talk about meshes, there are 2 sources of errors, okay, error that are associated with the discretization. Can somebody tell me, by intuition, which are these 2 sources of errors that you can actually come to your mind? Oh, sorry. Okay, I already did one. Okay, one is the approximation of the geometry. Okay, so remember that we are actually discretizing a continuum. So the first source of error is the approximation of the geometry. And the second one is associated with the accuracy of the solution. Okay, So with the approximation of the geometry, to basically explain you both of these concepts, no? I will consider a very simple example, no? So you consider an infinite plate that in this case I consider just 100 by 100, okay, for my simulations. It's not 100 by 100, I consider 200 by 200, no? With a hole of 10 millimeters in radius in the middle, okay? So this plate is subjected to a uniform, okay, pressure, stress of 4 megapascals to both ends, okay? And this is a plate that is made with a material with a Young modulus of 1,600 megapascals and a Poisson ratio of 1/3, okay? So the advantage of this problem is that if this is an infinite plate, it has an analytic solution, okay? So I know exactly what should I be getting. So I can actually always compare or quantify the quality of my, my numerical solution, okay? So in the geometry, I want to ask you a question. I will be a fem ophthalmologist, no? So you remember that when you go to the ophthalmologist and then he puts the glasses, no? Then he shows you a letter and say, do you see it well? You respond yes or no, and then ask you better now or no? And you say yes, and then he corrects and keep correcting these things, no? So in this case, we are going to do a similar exercise, but with meshes, okay? So imagine that we use Q4 elements. So Q4 elements are basically squares with 4 nodes, okay? So basically the edges or the sides of these elements are straight lines, okay? And I want to discretize my previous problem. Okay? So I use this coarse mesh here. So could you tell me which representation is better, this or this one? The only thing is that, you know, with this chat is really terrible because I don't see anything. Okay? So it's clearly, no, the one in the right, okay, is a better representation, just because I can see with the naked eye that this curve, which has to be a circle, is much better represented than here, that is an octagon, okay? Or it's a section of an octagon, it's a quarter of an octagon. Okay? And if I consider even I basically halve or double the density of the mesh, okay? I can see that in this case, I can represent this geometry almost perfectly. So to the naked eye, I cannot see basically a significant error between my discretized geometry and the actual continuum geometry. Okay, so when we represent complex geometries, we require a sufficiently fine meshes to properly approximate the geometry. Okay, and this is one thing that when we do the meshes, so that the first, you know, the first rule that we follow when building the meshes for an elastic solid, for a structure, is basically trying to see that our mesh is actually representing correctly the geometry. Okay. Usually, if we have high order elements, like for instance quadratic elements, okay, we may solve these problems in many cases. We may solve this problem. So in this particular case, if I use a coarse mesh with a quadratic elements, okay, I approximate the geometry exactly, even though in here it doesn't look like, okay, but it's just because of the software is not able to represent me the curve, but it's actually in the at the mathematical point when we solve this problem in the computer, okay, this curve is actually a parabolic curve. It's a quadratic. So this circle is exactly represented by these Q8 elements. So we have a much coarser mesh. Okay, this is a paradoxal, no? We have a much coarser mesh in which the error associated with the geometry representation in this case is 0. Okay. So this geometry, you know, error-free geometry elements has basically been responsible of having inspired the research of important groups of the one of Dr. Hughes in Texas, no? Where they proposed what is called these isogeometric elements that are able to represent exactly any geometry of the solid that we are solving. Okay, they use these NURBS or splines to represent any geometry such that the error associated to the discretization of the geometry is completely zero. Okay? However, there is a second component of the error. So in general, a reasonable mesh size that approximates well the geometry of the body can be decided by the naked eye. And that's something that we saw already, no? So, and this is takes us to another important message, no? Is that good sense, okay? So good sense is an irreducible element when performing finite element analysis. So if you are meshing a solid and then you see that actually the mesh does not reproduce accurately the geometry, then you know that that mesh cannot work, okay? Okay, so good sense is always a very important ingredient of a finite element analysis. Okay, so imagine that once that we basically know how to tackle the geometry approximation problem, okay, we basically use at least sufficiently fine meshes. Then we come into the accuracy problem, okay? That is the effect of the element size. So what I'm going to show you here are the results of 3 different analyses, okay? I have actually hidden the mesh characteristics, okay? But if you look at this solution, okay, these solutions look, pretty much alike, okay? So the stress gradient and the concentration, the stress concentration is very similar in all of them, okay? Actually, the value of the maximum stress you see on top is similar as well, right? However, you have to be very careful with this, okay? Because this is what you usually see in a finite element software, in a finite element solution, if you look with, if you don't look carefully at the solution. So you have to be very careful with what you plot. And this is something that we always ask to our students, is that when they look at the solution, you have to plot the things in a proper way in order to see if your discretization is accurate, is good enough or not, okay? So what you see on the bottom here is exactly the same solution that you see on top, okay? But without the trick that is used for many softwares, okay? So in the first one, on the top, what you see is basically the average of the stresses at all the nodes, all the neighbor node, is the stress plot in the node that average all the neighbor elements, okay? So what you see here is basically a representation that is clearly smoothing out the solution, okay? But most of that is smoothing out the maximum value of the stress. What is smoothing out is actually the discontinuity that you see between element to element, okay? And then you can see, looking at these, looking at the figures on top, you cannot really say which mesh is better than other, okay? You can intuitively, for intuition say, well, the one in the left is better than the one in the middle, okay? But you cannot really quantify that. Looking at the pictures on the bottom, okay, you can clearly see that the mesh in the left is clearly not a good one, okay? And the one in the right is significantly better, okay? The reason is because in finite elements, the displacements, which is a picture that you see here in the right, is continuous between elements, okay? Then the contours, okay, or the fringes plots of the displacement will be always smooth, okay? But the stresses, they are not, okay? So basically, what happened is that you can see in this element that the stress field is very, very different to the neighbor one. And when you have such a big discontinuity, like as shown in this picture, that means that your the quality of your mesh is not good at all. So when you see these things, this is asking you to actually increase the discretization of your mesh in order to improve the quality of the solution. Okay, then you can see that if you actually take a look, a zoom on the area of interest, you can see that as you increase the mesh density, you see that now your discretized solution is able to capture, okay, the gradient or the variations in the stresses better than in the case of the coarse mesh. Okay? So in the limit, actually the mathematical theory of finite element tells you that as the mesh size goes to 0, so if you actually keep increasing the mesh density here, okay, the stress field becomes, okay, you got a continuity limit in which you will be able, in your discretized solution, will be able to capture the gradients of the stress field, okay? Increasing the order of the element generally improves this behavior. So if you use a high order element, that means that you have a much better quality of interpolation of the solution inside the element. And then these elements are able to capture, these gradients in a much more accurate way. As you can see, if you compare, for instance, the solution in the middle on the top panel with the solution in the right-left panel, okay, sorry, in the right bottom panel, you can see that the gradient, the quality of the gradient of the stresses in the quadratic case is much, much better, so are smoother than the case of the linear elements. Okay? So usually the quality of the mesh is, so the previous exercise is very useful, okay, to at least as a first judgment of how good your discretization is. But if you want to perform a much more formal quantification of the quality of the mesh, you have to perform a convergence analysis. And a convergence analysis consists of monitoring a specific variable, okay? The changes of how this variable changes as you increase the node spacing, okay? Or basically increase the node spacing, reduce node spacing or increase the mesh density. Okay? So what we see here is basically a convergence analysis for a linear and a quadratic meshes that I showed you before. And then you can see that as the node spacing reduces, so as the mesh size becomes smaller and smaller, then the solution actually converges to an analytic solution that is around 12 in this case. It's around 12, yeah, it's 12, around 12 in this case. And a displacement that is close to 0.0267, more or less, okay? So a convergence analysis is a good, basically, I forgot the word now. Practice, okay, it's a good practice. But an evaluation of the quality of the mesh should also look at how well the discretization captures the variation of the gradients of the stress-strain field, okay? However, when we do mesh, okay, the convergence can be achieved at a lower computational cost with what we call a smart mesh, okay? And a smart mesh is basically a mesh that takes into account basically how is the strain field in my solid. So in this case, what we do is that we increase the mesh density in those areas where we have higher stress on the strain gradients, okay? Then if you do so, you can see that actually the convergence is greatly improved, but what is more important, the computational cost of your model is significantly reduced, okay? So in this case, for instance, when you do these adaptive meshes, or base specific or local mesh refinements, as the one that we did here, the idea of performing these operations is to basically maintain the number of degrees of freedom as contained as possible, so that we'll basically keep the total computational cost in somehow bounded, but we will increase the quality of our solution to acceptable values, to acceptable ranges. Okay? So at this point, I think the take-home messages that I wanted to give you, and this is perfect in timing for to just take us a short break, are these ones, not four. First one is that in finite element analysis, the element size matters, okay? So you have to use the right element size in order to basically achieve or obtain good solutions. Second one, good meshing is an art. So try to don't mesh harder, mesh smarter. So try to analyze your geometry, analyze your solution, and then improve your meshes in those places where they require it. Always look finite element results with a critical eye, okay? Do not become a color believer. Softwares nowadays, they produce very nice plots, very nice color, fringe colors, fringe plots, okay? Be careful with what you see, because not always what you see is the right thing, okay? And the last one, that is basically a phrase of one of my professors, when I was doing the PhD. If you know the exact solution, use it, okay? Forget finite elements, forget CFD, computation fluid dynamics, forget any numerical approximation. If you have the exact solution, use it, because the exact solution has no competition. Okay? Then, as I told you, the finite element application, the finite element analysis have found applications pretty much everywhere, okay? We found applications of finite elements in electromagnetism, in automotion, impact analysis, computational fluid dynamics, biomechanics, paleontology, okay? Finite element analysis is actually used to find how the dinosaurs actually bite, okay? The forces they were used to bite and during when the force in which they bite the victims, in biomechanics, we found applications in stenting, okay, in modeling the arteries, which is the example I will show you in a few minutes, but also in other applications, so like eye mechanics in the study of aneurysms, and for instance, electrophysiology in studying the electrical behavior of the heart. Okay? So now, just to finish this part, I wanted to ask you a couple of questions using also a Kahoot game, okay? Which just 3 short questions, just to see how if you were actually paying attention or not, okay? And then afterwards, I will open the presentation to questions if you have them. Okay? So let's wait for you to sign, okay? Okay. So let's start. So the first one. I'm sorry, I put the answer in Spanish. I'm sorry. It's yes, no, sí. Exactly. Good. Okay, because this is a typical I think the first exercise that we do in the strength of materials applications, no? So for the next one, who is this guy? Let's see if you recognize him. This is a very simple question because it's only one. Exactly, it's Richard Courant. And the last question, I think it depends on the application, right? But usually a mesh that is regular is a much better mesh for this for solving the problem. So the mesh in the left that was all homogeneous with exactly the same voxel size is generally better. Okay. Okay. If you have any question, then I'm open. Okay, to questions now. Otherwise, we can take 5 minutes, okay, or 10 minutes, and then I will come back to the second part of the talk, okay, which is basically an application in cardiovascular mechanics. Okay, we will see each other then in, let's see, in 5:45, okay? Okay. Okay, they tell me that, yeah, I didn't realize the time, which is 5:38. So let's take a couple of minutes. I will come back at 5:40. Okay, just I will get a glass of water and then come back, okay? Okay. So let's continue with the presentation. So what I wanted to do now is just to show you an application of finite element analysis in cardiovascular system, no? Cardiovascular mechanics. Right? So the problem of interest in this that I'm about to describe you is the modeling of the PTA, no? Of the percutaneous transluminal angioplasty. So the PTA, as you know, is or for those that don't know it, is the first step, the previous step before stenting in peripheral arteries. Okay. Usually in coronary arteries, the PTA is applied with the stent itself. Okay. So this is why it has been mostly applied to femoral arteries. The problem that I'm about to describe is actually associated, is related to this problematic in the SFA. So with the advent of drug-eluting balloons, basically PTA is becoming a potential treatment for stenotic peripheral arteries. So they are avoiding to implant the stent and then basically do the PTA with the drug balloon, drug-eluting balloons to reestablish the flow, as you see on the right. The problem with the PTA is that from a mechanical point of view, is a significantly traumatic process, okay? Because during the PTA, what we do is that we overexpand the lumen of the artery in order to, the idea here is to break the plaque, okay? And to reestablish the lumen. Okay? The only problem is that during this process, what happened is what you see on the pictures on the right, okay? So there is an extensive, significantly damage in the arterial wall that basically causes the restenosis. Okay, so this wound that is actually created after the PTA may favor the reappearance or the reformation of the restenosis. Okay? So what we wanted to do here was to we were trying to reproduce, okay, the damage caused in the artery during the PTA. Okay, so we were able to reproduce the damage, and in more particular, the delamination that has been observed in the artery during the balloon expansion. So in order to do that, what we did was, of course, we wanted to apply finite elements, okay? But basically, our first step was focused on proposing a damage model for the anisotropic tissue, okay? And this is something that I didn't talk about directly or in detail in the previous talk, but what we did was to formulate an strain energy function, a suitable strain energy function that was able to describe the damage of the tissue when was overstretched, okay? So we consider basically the anisotropy of the vessel, okay? So we consider two preferred directions, one circumferential and one longitudinal direction, okay? And we introduced what we call three damage functions. So we were considering allowing for a damage occur at three different elements of the arterial wall. So one is in the matrix, there's a cellular matrix that is actually present in the arterial wall, and damaging also the collagen fibers that actually reinforce these, reinforce the wall, and that give this anisotropic behavior to the tissue, okay? So these damage functions, I don't go into the details of these damage functions. So how is the formulation of these damage functions? But basically, these damage functions, they are formulated in such a way that they are only monotonic functions. So once the damage occurs, it is irreversible, okay? So we don't allow for the tissue to heal in this case, okay? And then using this formulation, we were able to reproduce the uniaxial test conducted in human SFA, okay? So we basically conduct this experimental test in the lab, and we feed our strain energy functions, our model, to this test in order to describe the tissue in appropriately, okay? So the next step was to implement these into a finite element software, and then we applied to apply this to a case of a study that we are actually currently analyzing together in collaboration with the University of Bern. So the model that we are analyzing is a segment of the surface femoral artery. It's a distal part, it's a distal SFA, distal section. Within this artery, you can distinguish the medial layer and the plaque. So we are actually leaving at the moment the adventitial layer out of the model. Okay, we are incorporating now, but the results of the model you are able to see consider only the media layer. And then, of course, the balloon that is used for doing the angioplasty. Okay, so let's see that the framework that we are using to conduct this finite element analysis is a framework of is hyperelasticity. Okay, so it's basically the same equations I showed you in the previous presentation, with the only adding element of this damaging mechanism that will allow us to represent the delamination of the tissue. Okay. But apart from that, are exactly the same governing equations that you saw before. Okay. So we incorporate also, as you see, the damage model only applies to the media layer. For the plaque that we use is we include also elastoplastic material with damage. Okay. In which basically we use experimental data reported by, I didn't put the name here, sorry, Kunane and co-workers, okay, that they did an extensive test on femoral SFA plaques, okay? So we use those models to incorporate in our finite element analysis, okay? In addition to the damage, what we include was an element deletion, no? So basically a fracture mechanism to allow for basically the lamination to occur, okay? So in order to be able to reproduce, okay, to model this rupture of the vessel during the expansion of the balloon. Okay? So the solution, okay, is okay, showing in this video. As I told you, this is something that we are actually doing with a master student. Okay? So you can see here the expansion. So when you see how the artery expands due to the balloon, and then how the artery actually bursts, okay, or breaks, fractures due to the action of the expansion of the balloon, okay. And then what we did was to actually compare, okay, our solution, no, with okay, with the results that are reported in literature, and also with the results from OCT analysis performed on that particular patient. Then what we were able to describe with the model was exactly the same failure mode that is present in the paper I showed you. No? I actually sent you yesterday. No? Is this the presence of this large spiral dissection that is present in the vessel, which is exactly the same one that you see here. Okay. Now what we are currently doing is, as I told you, adding the adventitial layer, okay, just to see if, of course, the adventitia is a much more compliant material that will prevent basically from this, let's see, the artery from completely burst, no, wide open as you can see here. But still the delamination will occur, so will be only limited to the media layer. So what we wanted to do afterwards is to compare if the patterns of fracture that we reproduce in our model are coincident or are in good agreement with all the different sections of the OCT of the patient that we are simulating. Okay? So the idea of this work is to basically find or basically establish better criteria for the overexpansion during PTA. So trying to maximize the lumen size that is reestablished after PTA while minimizing the damage induced in the tissue during the intervention. No? So the goals that we achieved in this simulation is we developed and implemented the damage model for an isotropic tissue in the finite elements. and we model the PTA on the patient-specific geometry. And this is very important, patient-specific geometry, because we don't know from these patients, okay, the exact characteristics of the tissue, okay? And this is a very important unknown and uncertainty in most of the analysis that we perform, particularly in biomechanics, no? The future work that is what we are actually currently doing is to complete the models, as I has told you, by including the adventitia layer. And we would like to perform simulations for different balloon sizes, okay, to quantify the damage and then validate the result with the clinical data. The idea is to apply later on this arterial dissection model to coronary arteries. And as you can see, we could also use this, the same approach, this technology, in trying to model the interaction, incorporate that to the interaction of the clot and the stents, okay, to simulate, for instance, micro ruptures or maybe the clot ruptures. Yeah? So with this, I conclude. Okay, sorry, I conclude the talk. If you have any questions, I'm open to answer them. Please let me know.
Can I just start?
Yeah.
So in this application, you have the mechanics of the balloon and the vessel wall, or do you take the mechanics of the balloon as a given fact, because it's usually way stiffer than the vessel wall? How do you do that?
You see the characteristics of the balloon, the pressure diameter. No, we calibrate the pressure diameter, the compliance of the balloon to the technical data of the balloon.
Okay, so what you apply in your modeling is basically a given strain all along the length of the vessel, because the pressure inside the balloon is extremely high, of course, and it will distend anyway, irrespective of the vessel wall mechanics. Yeah.
Basically, the interaction between the balloon and the artery is a contact. It's a contact. It's a contact interaction. So in the inside of the balloon, we apply a pressure that goes up to 12 atmospheres. Okay, and then yes, as you say, basically what we are doing, we are straining the artery, which is actually what happens, no, in reality. So you know, once I saw a student, and instead of doing this, it was applying the 12 atmospheres directly into the wall, and that is a completely different.
Not a good idea.
That is basically, that is a good example of bad modeling, no?
Yeah.
It's just the opposite. Yeah.
I tried this in reality with blood vessels, and they hold up to about 1 atmosphere. After that, they explode.
Exactly. Exactly.
Okay. Thanks.
Yeah.
Hi, Jose. Could I ask a question?
Yeah. Wabi. Yes.
Wabi, yeah. Sorry. I was wondering how you go from your OCT image of the vessel to the mesh. So what steps do you take to get to the meshing stage? Okay,
this is something that I'm going to show you the. Okay, so this step is performed by our collaborators in Bern. So they use a mira. Okay, so they segment. What they basically do is that they segment the image. Okay, and once that they segmented the image, they discretize the image directly. Okay, with the segmentation software. It's similar to what Mimix does, and many other softwares as well, Beta. I don't know if it does it for cardiovascular, but Amira is similar to Mimix. Okay? So what we did with this example is that we generated. First of all, what we are doing now is to put everything. We want the pipeline to work. Okay, and then we generated 3 different meshes. okay, with 3 different densities, just to make evaluation of the impact of mesh size in this particular problem. That's the next step.
Okay.
But it's performed separately. So we have the segmentation software. They do the discretization and then generates save the mesh in the format of the software that you will use for the simulations.
Okay, thanks.
Hi, Jose. I have a quick question. Very
Yeah.
nice presentation. Is meshing only applicable in macroscopic level, for example, can it be used at microscopic level as well? If you're trying to study cell biomechanics or other things at cellular level, is it possible?
Yeah, depends on it depends on if the continuum scale is still usable for your application. No?
Okay.
For instance, when you in bone modeling, bone mechanics, okay,
Yeah.
what is usually done is called FEM square, FE square, okay. So what you do is the following. So you take a representative unit of your trabecular bone, okay, and then you apply a set of well-known loads, no, like for instance the 6 deformation, and then you homogenize what you find at that stage, okay, in order to find the mechanical properties that you apply later at the mesoscopic scale.
Okay.
This is called finite element square, okay, FE square, and it's called multi-scaling also. Okay, so in this case, you are using the trabecular bone, you are describing with finite element the microscopic scale, and then use this result to apply later on to a mesoscopic scale. The same thing for the cells, no? For instance, we have used finite elements to describe to model the diffusion of the diffusion of nuclear, how is it called, substance, no, the passive diffusion of substance into the nucleus of the cell, okay, and then you use finite elements, even though if you think, you know, that at that scale the continuum mechanics is still not applicable. Okay, but what you find out is that when you're running these FRAP experiments, no, in which you bleach the nucleus and then just measure the recovery of the nucleus, no, what you find is that basically the a diffusion equation, okay, is able to describe this recovery nicely, no, at the nuclear scale level.
Thanks, Jose. That's very good.
Any other question?
Okay, I think it was very informative. I would like to thank you, Jose, for explaining these methods to us. It's, I guess, for most of us, it's not something that we will use ourselves in the near future, but it's very good to know that these techniques exist and get some idea on how to apply these. Okay, thanks very much. It's 6 o'clock.
Right.
We have to stop.
Okay.
Okay, thank you.
Bye.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.